All right, on Monday, we finished up talking about the production of urine and then the release of urine through the process of micturition. What we want to do, or what I want to do here for the last couple slides, is just briefly talk about some stuff that we've talked about at various points this semester, the importance of maintaining a normal pH. So, reading through a major homeostatic challenge is keeping our hydrogen ion concentration or our pH of body fluids at an appropriate level. Without the maintenance of an acid-base balance, normal cellular function wouldn't exist. Remember, from all the way back at the beginning of the semester, that proteins prefer a specific pH, as well as temperature, to keep from denaturing. Denaturing, remember, I've kind of always used the analogy of when a slinky becomes uncoiled, it no longer will, go down the stairs. So it's important that proteins keep their shape because that affects their function. A normal healthy person must maintain the pH of their systemic arterial blood between 7.35 to 7.45, which is slightly basic. Remember, 7.0 is neutral, so 7.4, which is right between those two numbers, 0.35 and 0.45, is what we like to see it. It's really just very, very slightly basic. Removal of hydrogen ions from body tissues or body fluids is, and subsequent elimination from our body is dependent upon three major mechanisms. The first one are buffer systems, which utilize buffers that act quickly to temporarily bind to hydrogen ion and remove it from the solution. They will help raise pH of body fluids, but won't actually remove hydrogen ions from the body. Protein buffer system is the most abundant buffer in our intracellular fluid and our blood plasma. Amino acids making up these proteins are capable of releasing hydrogen ion when pH rises. This hydrogen ion can then combine with hydroxide, OH negative, forming water. The other end of amino acids are capable of combining with hydrogen ion when our pH falls. Carbonic acid bicarbonate buffer system is something that we've talked a lot about here lately. It's based on the bicarbonate HCO3, which can act as a weak base, and carbonic acid H2CO3, which can act as an acid. So we will affect those levels based on the state of pH. And then the phosphate buffer system utilizes various forms of phosphate ions, regulating acid-base balance in our cells, in the cytosol of those cells. We talked in our last unit about CO2 and its relationship to pH. Remember that CO2 will combine with water, and that will dissociate to form an acid, so we can affect our pH by changing our breathing rate. Okay? Remember, we have two basically descriptions of breathing rate, hypo and hyperventilation. Hypo is low ventilation, so we breathe less, which means less CO2 is exhaled. Therefore, hydrogen ion concentration will increase and pH will drop. The opposite is what occurs when we hyperventilate, which causes more CO2 to be lost, which means also hydrogen ion will decrease and pH will rise. Okay. And the final thing, and this is something that we've been talking about here in this last lecture, or this lecture, not our last lecture, is how our kidneys can excrete hydrogen ion. This is the slowest mechanism, but it's the only way that we eliminate acids other than carbonic acid from the body, and it is through our urine. If we fail to maintain pH, we can have one or two imbalances occur: an acidosis or an alkalosis. An acidosis is a condition in which blood pH is below 7.35. That's what we're showing over there on the right. Major effect of acidosis is depression of the central nervous system through depression of synaptic transmission. So it prevents synapses, which is, remember, where neurons can release neurotransmitters that communicate with another neuron. This can cause a person to fall into a coma and can possibly lead to death. Alkalosis is a condition in which blood pH is above 7.45. Major effect of alkalosis is overexcitability in both the central nervous system and peripheral nerves, which can cause nerve impulses to be conducted repetitively even when they're not stimulated. This can cause nervousness, muscle spasms, and even convulsions, as well as death. Now, we can counteract alkalosis and acidosis, or acidosis, in a process called compensation. There's two different forms of compensation. One that involves breathing changes, We call that respiratory compensation. And this involves regulating our blood PCO2. If we increase blood PCO2, we'll lower pH, whereas we'll decrease blood PCO2 to increase pH. Okay. What takes much longer is renal compensation. So this is important in long-term acid-base balance, where we regulate our blood bicarbonate excretion or concentration by reducing the rate in which we excrete it when our pH decreases, or when our pH increases, we increase the rate of bicarbonate excretion. Okay. Over there on the right, they're showing a feedback loop, and this is actually a feedback loop we've seen before that looks at how we perform respiratory compensation, which is where we're increasing breathing rate. That means we blow off more CO2, which helps to bring our pH up after it's dropped down. Okay. So that on the right is respiratory compensation, not renal compensation. Table 27.4 here shows actually two different forms of acidosis and two different forms of alkalosis. Okay, so there's four different kind of conditions that can develop. Respiratory acidosis is where there's an increased PCO2 and our pH drops. We can have this occur from things like emphysema that results in hypoventilation, pulmonary edema, trauma to the respiratory center, airway obstructions, or dysfunction of muscles of respiration. So basically, a lot of it has to do with our lungs not able to breathe off enough CO2. And whenever we have a respiratory situation, we'll respond with a renal compensation. Okay? So we would increase the excretion of hydrogen ion and increase the rate of reabsorption of bicarbonate, and that should bring our pH back to normal. The figure on the bottom left actually shows what we can do in response to these various conditions. So what we want is point A, and if you draw a line down from point A, our blood pH would be 7.4. If you draw the line to the left to meet the y-axis, we're going to find that bicarbonate is around 26. I'm not even going to get into that abbreviation or the units. We'll just use the word or number 26. Okay, so respiratory acidosis is going to cause our pH to drop. So in respiratory acidosis, we go from point A to point B. And if you draw a line down from B, we've gone down from 7.4, probably somewhere on 7.3. We compensate by increasing our blood bicarbonate, which means that that's going to go up. And so point D is where we end up, and we're back at 7.4. Okay. Now, you'll notice that we've also changed from 40 millimeters of mercury of PCO2 to 60. Okay, and that's what caused the whole issue in the first place. Okay, our CO2 levels have gone up. Okay. The opposite of respiratory acidosis is respiratory alkalosis. So it's like going from point A to point C. Our pH has gone up. Our PCO2 has dropped. We compensate by excreting more bicarbonate, so our bicarbonate levels in the blood will drop. Okay, and that brings us to point F, and that's back at 7.4. So you'll notice that we always want to strive to get back to 7.4, but that might mean we change CO2 levels or bicarbonate levels to have that occur. Okay. Then you've got metabolic acidosis and metabolic alkalosis. Acidosis is like going from A to G, and then compensating by changing our breathing. We breathe off more CO2, so our PCO2 drops to 20, so we end up at 7.4 at letter F. And then alkalosis is where we're going from A to E to B, and we have respiratory compensation by hypoventilating. I'm not going to get into any of this for the test or anything like that. Just kind of cool information, and I like the figure because it kind of shows you what our body does, kind of in a simple way, yet it's kind of still pretty complicated. Over on the figure here, letter A is showing you how we can get rid of hydrogen ion into our tubulin. This is the same figure that we saw pretty much anyway the other day when we were talking about the various aspects of urine formation. And then the figure on the right is just showing you how simple it is to cause a pH to drop or a pH to rise. And pH drops can occur due to accumulations of acid, and or losses of bases. And then pH rises, alkalosis can be as simple as a loss of acids and or accumulation of bases. So nothing too earth-shattering there, hopefully. Okay, any questions on